to talk about a work from our lab, which actually uses signal decomposition with sensor fusion to reduce the motion artifact in intra-oral EEG signal. This work is mostly done by my PhD student, Shibam. So this is the outline of the presentation. So first I'm going to talk a little bit about the intra-oral EEG measurement that we have done previously and the measurement system, and why we actually went for the motion artifact removal. And then I'm going to talk about the algorithm that we used to remove the motion artifact, and then conclude the presentation. So I guess more or less we all know what EEG signal is. So this is really the biopotential that is developed around the brain, and normally the electrodes are placed on scalp to measure this EEG signal. So EEG signal has many applications from different like health diagnosis to even now human machine interfaces. So people also have shown that since the palate region inside the mouth is close to hypothalamus region, so EEG signal can actually be acquired from the palate region. So EEG signal is very small biopotential, so something in between from 0.5 microvolts to 100 microvolts range. So we need a very sophisticated data acquisition unit to acquire the EEG signal. And the useful bandwidth is somewhere between 0.01 to 200 hertz. And normally we divide it in different bandwidth and say like, alpha wave, beta wave, so we give different names. And depending on application, we focus on the different band of this EEG signal. So previously, in our previous work, we have actually shown that we can detect the intra-oral EEG signal from the palate region. So we developed electronics where we place these printed electrodes in a smart mandibular device in the palate region, and the electronics around this region to detect the intra-oral EEG signal. And why we were interested for intra-oral EEG signal is mostly for the sleep apnea patient, because a lot of sleep apnea patients wear a smart mandibular advancement device, which helps them to breathe better during sleep. And doctors want to actually see how well they're sleeping while they're using this treatment option. And one of the things they like to see is the EEG signal. So this actually motivated us to incorporate this idea that whether we can get the EEG signal from the palate region. So as I said in our previous work, we demonstrated that, okay, we can get the EEG signal from the palate region. But one thing to also mention here is because the palate region is not a large area, so we can only incorporate, only few number of electrodes here. So in our system, we only use a one-channel EEG signal here. So what we observed is when we monitor the EEG signal, also because it's a biopotential, so it gets disrupted by different motions. And intra-orally, we have different types of motion like tongue movements, teeth grinding, or gulping. So all of this actually affects the biopotential or the EEG signal intra-orally quite a lot. So we also incorporated an accelerometer in the electronics part. So I think it'll be more. So this is actually the electronics part where we have the data acquisition unit and the signal transmission unit, and also an accelerometer here to basically the accelerometer detects when the motion happens intra-orally. So yeah, so we have this electronics. We know, okay, we could see that the motion is happening from the accelerometer data. And we also see like when the motion happens, the intra-oral EEG signal gets, disrupted. So what do we do about it? So that's actually what I'm going to present here. So this is really the hardware we use. So we have a mandibular advancement device that people use for sleep apnea. And on the palate region, we, around that area, we place these flexible gold electrodes to get the EEG signal. And these electrodes are interfaced with the analog front end that is in this region. And also here we have a accelerometer, which is also interfaced with the analog front end. So the analog front end processes the signal and sends it to a microprocessor Bluetooth unit for and sends it wirelessly to a computer. So this is really so this is actually the data acquisition unit or the analog front end we actually developed by ourselves. So basically it has some gain, some filters, and again, also the accelerometer data that also goes through some gain, and then the signals are sent wirelessly to a computer. So it's nothing really very special in the hardware. There is also a power supply module that, with voltage regulator, it just gives us different DC voltages required for the electronics part. Okay, so what I'm going to talk about mostly is how do we remove the motion artifact. So with this hardware, we acquire the accelerometer data and the EEG signal concurrently. So the EEG signal is a single channel EEG signal. So once we gather, when you gather the data, so first we look at the accelerometer data. And from the XYZ component of the accelerometer data, we calculate the resultant. And then we detect the envelope of that resultant. And we look at the value of the envelope. So we found that if there is no motion, the envelope value is below 40 millivolts. So we actually check whether the envelope value is below 40 millivolts. If it is below 40 millivolts, we know that there is no motion. So we do not do anything with the signal, EEG signal. Now, if we see that, okay, there is a motion, so we see the envelope value is greater than 40 millivolts, then we actually find the time location where the intra-oral motion happened. And one thing we also noticed is, okay, so when the motion actually stops, the disruption in the EEG signal doesn't go back to the base value immediately. It takes some time for the biopotential to settle down to the stable value. So once we know the duration of the motion, to account for that time for the electrode biopotential to settle down, we put some cushion around the time range. So our actual time range, so the time range that we consider is a bit higher than the actual time range when the motion happens. So we know this time range. Now, what we do with this time range? So we have this intra-oral EEG data, and what we do is, if we see that, okay, there is a motion that happened during that collection of the EEG data, we decompose the EEG signal into using the discrete wavelet transformation. We decompose into 10 wavelets. And then each of these wavelets, again, we through the fast ICA algorithm, we generate 10 independent components or ICA components out of this wavelet. Now, we also know the time range where the motion happened. So we map this time range in this independent component that we got from the EEG signal. And when we looked at this independent component, we saw that the first 7 independent components are not that much affected by motion. It's the last 3 that are affected mostly by the motion. So for the first 7, what we do in this time range is we apply a thresholding method to basically compensate for the motion artifact. And for the last 3 components, what we do is where the motion happens in that time range, we actually set the value 0 for the EEG signal in those locations. So then we take again back those 10 independent components, do a inverse ICA and get the wavelet, and then again do a inverse wavelet transformation to go back from the wavelet to the EEG signal. So this is again explaining the same thing. What we did is basically decompose the EEG signal into 10 wavelets. So if we actually can use more wavelet, we can get better performance, but it also increases the computation time. So this is an example. I mean, not all the stages, but at the first row, you can see the EEG signal for 3 different intra-oral motions, so tongue movement, teeth grinding and gulping, and the blue locations are where actually the motion happens. And these are the accelerometer resultant data, and this is really the envelope. So you can see when in the envelope of the accelerometer, you can easily detect where the motion happens. So from this time range, we apply all those signal decomposition techniques and then get the motion artifact-free EEG signal. So this row actually shows that inside the blue box where the motion happened, the motion artifact was reduced, and the last line basically shows the signal we had with motion with the signal where the motion artifact was reduced. So that gives the comparison of the reduction of the motion. We also did some quantitative analysis. So basically, here you see one data, and so basically this hardware was used by 3 volunteers, and from each volunteers we took 9 sets of data for 3 different types of motion artifacts. And we actually saw how much actually the signal to noise ratio reduced after we did the motion artifact removal, because when you have the motion artifact in your EEG signal, your signal to noise ratio is higher, and when you do the removal, you should reduce the signal to noise ratio. So you can see for teeth grinding and gulping, the signal to noise ratio after we do the removal reduced quite a bit. But for the tongue movement, it's not much. And the reason for that is also because the tongue movement, if you even see the signal with the motion artifact, you see that the tongue movement doesn't add much artifact to the EEG signal. So in conclusion, we actually have one method that can reduce the motion artifact for the single channel intra-oral EEG data. So in future, what we plan to do is also to look at other signal decomposition techniques like EMD and ICA or EMD ICA and optimize, see like which algorithm actually performs better with this technique. And we also would like to monitor it with more subjects, because right now this was only done on 3 subjects. So in future, we'd like to monitor more subjects with this method and see the validity of the technique. So that concludes my talk, and if you have questions.